Hello all, Luke again with the next session on category theory and functional programming. Prepared a worksheet to kind of recap what we did in the previous session, so let's uncomment this here. And this was our first version of factorial, which I'm running, and the result is of factorial 10 is indeed what you would expect. We transformed this factorial to two other versions. One version that illustrates expression evaluation, and another version that illustrates functional programming combinators, so to speak. Let's first start with the more operational thing, expression evaluation. Here are the two relevant supporting capabilities. First of all, the idea of evaluating an expression is of course to yield a result. For functions, we just encode this using the identity. And another capability is that once you have evaluated a sub-expression to a result, then you should be able to bind that result to a function where that result is available as a nested parameter or local variable, if you wish. That brought us to this version, which still runs fine, where we read the following. So we evaluate the expression n is equal to 0, yielding a result which you bind to b. And if b is true, just yielding a result 1. Otherwise, a kind of three nested things, evaluate the result, evaluate the expression n minus 1 to a result, bind it to q, evaluate the expression factorial q to a result and bind it to r, evaluate the product of n with r, the result of that one, bind it to s, and then the result of the whole expression is s. So those two capabilities, so to speak, completely capture the notion of evaluating expressions. But then we wanted to go one step further and work with functions instead. For that, we needed some extra capabilities. First of all, and I'm going to put this one here. To start with, an identity function, a generic identity function, which is called z to z, and this generic composition function, which is given the name, symbolic name, this arrow. So we have identity and composition, sequential composition. Then the next thing we needed was construction or product. So in order to deal with more complex data, we needed to construct products and a corresponding operator. And then in order to deal with complex algorithms, more precisely if then else logic, we needed sums. In this case, our sum is the sum of a left z and a right y, and a corresponding sum operator. Okay, so we then defined a few helper functions, because everything will be functional. Helper function is 0, helper function 1, helper function subtract 1, helper function multiply. And then what we didn't deal with in last session, which I will now deal with in a little bit more detail, we introduced in terms of product for the let-in combinator. So what this actually means is, well, you let, given a z, from that z using a function z to y, you produce a new local variable, so to speak. So now you have the z and the y, and the idea is, as opposed to sequential composition, that your z is not lost. And if your z is not lost, then you can use it in the in clause as a function with the function from z and y to x in order to yield a function from z to x. And how does it work? Well, remember we have the construction from z of our local variable or our local value, but we also have the identity, remember? And so if we have both, if we just use both of them, then from a z we can construct a z and a y, right? So that's what we do first. So from a z we can construct a z and a y. But now we have something with a z and a y that can turn that into an x, so we simply compose sequentially those two, and that's it, right? I hope that even the highlighted expression, apart from all the type annotations, kind of gives you a clue about what has been happening here. A similar thing holds to define if-then-else logic. Frankly, I'm not going to go in all the details here, I'm just going to take it for granted, but it's a very similar thing. Basically, the if-then-else logic that we encode in a library eventually will make a choice between a true case and a false case to turn a W in this case to a Z. It's a little bit of a tricky situation, but believe me, it just works. By the way, notice that in order to define it, we do need the let construct itself, right? So now that we have everything in place, we can define our next version, which is version 15, and just see if it also works. And of course, this will also result in the right value. Okay, so that's nice. To recap, what was needed was identity, sequential composition, construction, and condition. All right, let's continue with the next steps. I'm just going to do live coding with all the advantages that you can see me fail. So let's continue. Of course, I'm going to do a little bit of copy pasting. So the next thing we do is we make a new package called Specification. Where we are going to specify what a program is in terms of the things we've seen before. So let's make another folder, program, and in this folder let's create a file called program Scala. Okay, I prepared some code which I will now copy and paste. So what I will do here is just in that package make my thread program. Maybe it's a good idea to have my terminal back and see if everything still compiles. So far so good. So we've dealt with functions so far. Now we are going to deal with arrows. It's a type class for arrows which have an input which is contravariant and which have an output which is covariant, or maybe said in another way, which will have arguments that are an argument, that is contravariant and a result that is covariant. It's in sync with the Liskov principle that there's nothing wrong with requiring less and providing more. Okay, so what was our first capability? The identity. So let's introduce here a new folder, identity, and here a new file, identity. Okay, again a little bit of copy pasting. Here it is. So we have encoded the capability, a specification for the capability that there should be something like an identity arrow, let's say, and that from a Z turns a Z into a Z. Oh, by the way, we are going to add a few extra things. Namely this here for program, and we are going to do that consistently, and this here for identity, exactly the same thing. What are those used for? Well, they're just introduced to be able to use expressions, program such an arrow instead of implicitly. So a little bit of syntactic convenience. But the other thing we are going to do is, of course, we are going to already specify that programs need the identity capabilities. And therefore, we are going to import the identity thing here. And instead of copy pasting, I might as well extend then dt. Voila. See if it still compiles. Okay, so far so good. Okay, I told you that I like these fancy names, but of course, even if you work with generic capabilities, not everything is a Z. So it's convenient to have a few more, and I will just add them. And you can add as much as you want by need, wherever you want them. Well, y to turn a y into a y, it's exactly the same generic function, but just a more convenient name. Xx to turn an x into an x. And then a special one, maybe I should put here dots, but for unit, the unit type, which is not generic, you see, I reserve the UU notation. Okay, so far for identity. So we've now specified that programs need identity capabilities. What was the next one? Composition. Okay, so let's folder composition. And a new file. Okay. And do a little bit of copy pasting. Okay, so this shouldn't come as a surprise. If I can go from Z to Y and from Y to X, then I can also go from Z to X. And I have kind of consistently used this notation, and the same for this thing. And then of course we add to our program composition, and we can here write with some of you will recognize that what we have been specifying so far is that programs form a category, right? So here is the first relationship already with category theory. Now there is some capability we didn't even talk about in the introduction, namely that functions are programs. We took it for granted, but of course we are going to have to specify that as well. The least you can expect is that functions are programs. So let's make a new folder function with a corresponding new file function. And copy paste the function capability or requirement, if you like. That indeed, for every function, with every function corresponds. I will consistently call them arrows, an arrow, right? Now, of course, this could be the end of the story. You could say, like, okay, we just do functional programming and then turn them into arrows. But the whole idea is to have more flexibility than that. It will become clear from the rest of the sessions. Let's do also an import of this one. And then say that it also extends. Okay, I made an error here, no problem. There's something not okay. here. What did I do with function? PDP, specification, function. I think I see what I mean. There is a little bit of a problem because, of course, functions already exist in Scala, but now there won't be any issue anymore. Okay. Good. What's next? Construction. So, but before doing that, hey, we can add something to our specification, namely the following. Well, let's first define a function here, which is the identity function. Remember, we have seen this identity function in the introduction, and we are going to import that in our program to define a default definition of the identity. So if it's not overridden, then of course looking at the identity function as an arrow is what you would expect to be the identity arrow. Everything fine here. So let's continue with construction. Here we go. So again, our type alias, which is just convenient. And indeed, if I can construct a y from a z and an x from a z, then I should be able to construct a y and an x from z. And the same convenient object thing here. Now, let's add a few projection functions here, just like you had the identity function in the function file. We are going to introduce here projection functions. Project z and a y to a z, project z and a y to a y. And once we have those, we can import them in our program stuff. But before doing that, I'm first going to import the right stuff. Extend construction. Of course. And then have the corresponding construction arrows. Okay. I hope this is okay. No, I also have to import, maybe I should do it like this, the type which is otherwise not known, and here we go. Okay, so now we also have projection arrows. Nice. Let's move along and do condition. Same story. Just like construction is based on products, conditional logic is based upon sums. Here they are. And yes, if from a y I can construct a z, from an x, then from a y or an x I can also construct a z. Same thing. Probably I need also condition and the type, if only for symmetry reasons, and I can do this. And you will probably not be surprised if we've added for construction projections that we can add for condition injections, so let's do that. So we can inject a z into a z or an y, or we can inject a y into a z or a y, just on the left hand side or on the right hand side. No big deal. And then we can just kind of promote those things to arrows. Okay, yielding this and this. We are not done yet. Well, maybe mathematically seen we are done, but of course we want our Scala DSL. We want to be able to write nice programs. So let's move along with that. So just like we did in the introduction for construction, we can introduce here our trade in and our definition z, but of course we need a zz here, so we are not going to do that here. Well, we could, but in fact I'm a little bit lazy. We are going to do it at the level of the programs. Voila. So here is our in and our let, and you probably won't be surprised if we can do the same with the if then else. But we have to do a little bit more work. We first are going to put this function, because we needed that in the introduction as well. What is this function? Well, in fact, it combines a value with a boolean, and if the value is true, then, if the boolean is true, then we introduce it at the left. If the boolean is false, then we introduce it at the right, which means that we can also turn that into something which we put in our program. Let me see what I have to do. It will become clear. Let me just start with doing this. It's probably not enough. But the compiler will complain. It's not too bad. No, it's not possible that this is going to be okay, because I have used this one, which I don't know yet. So actually, it's okay. Here it is. I need this one as well, which is the lifting of that special function which I just introduced. And then probably it will compile. This one, WB to B, W and B, okay. Let's just see what happens. No, it doesn't have the same type. Oh, I actually had put it in already. Yes, I'm so sorry for that. I had put it in already. So here it is. I can safely do it away. I found it strange already that I didn't see any errors. Excuse me. So here it is. And the compilation will be okay now. Right? So, just like in the introduction, let's recap. We introduced a little helper function here, and then do the import like we did normally. So I will put it at the right place now. It's just another kind of special function, and then we can do our if then else DSL stuff, and that's it. Okay, so we are ready for our next example, which is the example of the factorial in terms of the specifications here. Now let's have a look. We need a little bit extra stuff here, which is this here in our SBT file, because we worked modeler. I need, let me just do that away a little bit. Specification. right? And frankly, I'm going to switch to my terminal because I have to do a little bit more work here. Okay, make there. And I should have done that. So the source, make there. Source. The main. Scala. All right. Program description based programming. And now copy -R. The whole specification thing, we have to kind of copy that to specification. I think I've done it right. Yes. Okay, maybe now this one will look a little bit strange. Hopefully not. Yes, makes sense. Let's close a few things. Close all. And let's go back to my program thing. All right. See if we did it right. I hope so. Now it should actually do 2 projects. I hope nothing's wrong. Yes, good. Why do I do this? Because I want to make a third one. So motivated by the success, I'm now going to make a third sub-project, which I call examples. Right. I'm going to make there -p examples source main Scala pdb examples. Right. Plus, I have my examples sub-project as well. I don't see it here. Yes, here it is. And let's move along. I think I'm ready now for continuing. I'm going to here write specification. Well, I'm going to write an example, and that's very important at the specification level. The specification level of programs, and it will be the factorial one, so it's really important to stress this here. I'm programming to a specification. Let's write here it's maybe a little bit too far in this direction, but a new file, tutorial.scala. And here's the good news, okay? It was a lot of work to make those sub-projects and stuff like that. But here's the good news, you will simply see what you've seen before. Here it is. Okay, so yes, it's almost okay because I also need the utils, right? So let's the 0, the 1, subtract 1 and multiply from the introduction. So let's here construct a new folder utils with the file utilscala. No, with the folder, excuse me, programming utils. No, program utils, excuse me, with the file utils scala, and there we put our friends that we already know. First, our functions. And next are programs, but of course we also need a little bit more, which I will tell you in a minute. Here are the programs, but of course we need our package and the corresponding imports. But that's not a lot, it's just our package here. The package for, well, because it's in the right location. For Scala it's not necessary, but I'll do it anyway. Then I need my construction operator and I need program specification, and it looks better now. Now let's look at factorial. Well, that's maybe the IDE who is not really happy, excuse me. But I would expect that it compiles now. No, wrong number of parameters. I know what this is. It's actually related to the newer version of Scala, which is kind of cool. So you can see me fail. I think I am obliged to write explicitly the case here. I hope that's the only thing that goes wrong. Now I know what it is. Well, of course I have to say that this depends on specification. Alright, so let's do our SBT again. Maybe clean things up, why not? And compile. Success. I'll just try. Maybe this was not even needed, but I'm not 100% sure. No. Alright, this finishes my second screencast.